All right, video number 3. Now we're going to get out of the Earth and into the atmosphere. Again, this is all about the Earth systems and resources for this unit. So now we're going to look at the upper part of our planet. We already talked about the lithosphere and the geosphere with the tectonic plates. We talked about right at the surface with soil. Now we're going to go up into the sky and look in the atmosphere. So this video is going to cover the Earth's atmosphere, global wind patterns, solar radiation and seasons, and then how the Earth's geography affects the climate. So go ahead. I'm going to start right off the bat with you guys pausing the video and coming up with answers to this. I want you guys to pause the video, list the major gases found in the atmosphere and what percent composition they're in. Then I also want you guys to pause and list the layers of the atmosphere. All right, hopefully you guys had a chance to do that. And when we look at this, we have N2, O2, and then mostly other gases, mostly argon, but some CO2 as well. And when you guys did your percent composition, hopefully you remember that it was 78% nitrogen, about 21% oxygen, and about 1% everything else. Again, carbon dioxide is not the number one other gas. It's mostly going to be argon, but there is carbon dioxide as well, and that's on the rise. We're putting more carbon dioxide into the atmosphere than we ever have before. Excuse me. So the relative abundance of carbon dioxide is increasing in our atmosphere. Now, oops. What did I do there? Sorry. When we look at this next part, the layers of the atmosphere, troposphere, stratosphere, mesosphere, thermosphere, exosphere. When we look back and think about those, try to remember what's the important stuff that's happening there. In the troposphere, what's important is this is where our weather occurs. In the stratosphere, hopefully you guys remember and can tell me that this is where the ozone layer occurs. Mesosphere is where meteorites burn up. Thermosphere, the aurora borealis and aurora australis, and the exosphere, that's outer space. So how do we know these are separating the way they are? Pause the video, try to remember back to how we know for sure that these are the layers of the atmospheres we have. Hopefully you guys remember back again that we have it based on temperature changes. In the first part of our planet, if this is the Earth's surface, and we're increasing altitude as we go, we see the temperature is going to be on the X, altitude would be on the Y, and we see a decreased temperature to start. Sorry, let me go backwards here. We see a decreased temperature to start, but then it pauses and starts to increase. Then pauses again, starts to decrease again. Pauses again, starts to increase. That's where we know we left the troposphere and went into the stratosphere. The next time it changes, that's where we know we left the stratosphere, went into the mesosphere. Next time it changes, that's the mesosphere into the thermosphere. That's going to be the way that we remember which layers are which. It's all based on temperature changes. And again, voila, we had the big video with it. So it's important to note when you're looking up here, Mount Everest, tallest mountain on the planet, it still is not into the stratosphere. We're still in the troposphere when we're in Mount Everest, but our temperature is getting much colder as we go. So as we're increasing with altitude, we're getting a much colder and colder and colder temperature. Then when we get in the stratosphere, due to the ozone layer absorbing that ultraviolet radiation, it's actually going to release that heat into the atmosphere above it. So we have a decreasing temperature because now we're losing that warming of the planet. The sunlight comes down, hits the planet, and warms up the planet. So as we're getting further away from that warm surface, it gets colder and colder and colder. Now in the stratosphere, that ozone layer acts sort of like that Earth's surface. It's absorbing the ultraviolet radiation. So as we are closer to the ozone layer, we have our warmest, our temperatures start to warm up again. So as we're moving upwards, we have UV radiation being absorbed the entire way through. So the temperature is getting warmer and warmer and warmer as we're going up, because this is maximum ozone, but the ozone layer kind of goes through the entirety of the stratosphere. So we end up with warmest temperatures nearest to the top of the stratosphere, coldest temperatures near the bottom. And again, that's due to the fact that it's really cold air underneath it. It has to heat up the air as it goes. Then when we get into the mesosphere, again, temperature declining again. I don't really care that you guys know that stuff in here. They're going to focus primarily on the stuff that's concrete to you guys. but know that the temperatures do change and fluctuate back and forth as we go. This part right here where the weather's occurring, this is probably where they're going to ask questions about. And that's what we're going to focus our video here on. So when we look at that reason why that temperature change happens in the troposphere the way it is, it's all about insolation. And I color coded this word because insolation stands for the incoming solar radiation. And that's how you can remember it. So in is incoming, sol is solar, ation is the radiation. That's how you can remember what insolation means. So this is basically the amount of energy coming to our planet. And again, our energy coming to the planet is in the form of heat. It's going to be that radiation that comes down, hits our solid objects. If the albedo is gives it the ability to absorb that energy and not reflect it, that's going to allow us to warm up. So when we look at that incoming solar radiation, it's different in different parts of the planet. So when we look at this graph, I want you guys to pause the video here. This picture here, they're going to be really big on showing you a model, which is what this is, and having you guys describe or explain from that model. So what we see here, we have our net radiation in watts per meter squared, energy per area. So when we look at it, let this part down here go away from it. The blue are going to be lower numbers. The reds are going to be higher numbers. So when we look at it, the redder it is, the higher the amount of energy per area. The bluer the color, the lower the energy per unit area. So what I want you guys to do is pause it and describe and explain the pattern you see in the image. So not that you want to describe the pattern, what's happening, but you want to explain why it's happening that way. That's the explain part. So go ahead, pause the video. Let's see what you guys get. All right, so hopefully for you to describe, the pattern that you're saying is when I look at the equator being here, as I go further north or further south from the equator, the amount of solar radiation per unit area is decreasing. That's the describe part. Describe is just telling what's happening. So in this case, what's happening in this diagram is traveling north or south from the equator, which is 0 degrees, I'm having a decreased amount of solar radiation per unit area. My explain for that, that's where I'm going to tell the why or the how. So my explanation for this is where, again, if you guys remember back to when we talked in class, the energy is hitting more directly at the equator than it is at the higher latitudes. As you increase latitude, either north or south, the energy is hitting at a much larger angle. The larger the angle the energy is hitting at, the more dispersed the energy is, thus lowering the amount of energy per unit area. That would be your explain part. So hopefully you guys were able to do that. And when we look at this, this would be the explain. This is why it's happening. So again, at the equator, the sun hits almost directly. Think back to the activity we did with the flashlights and the dowel rods, and we adjusted the angle. So at the equator, it's hitting almost direct. So we can see that sunlight is very, very concentrated, high energy per unit area. As we increase our latitude, we can see this is almost the same as the equator, but it's dispersed and it's a bigger area that it's spread out over. Same quantity of energy coming in, just spread out over a larger area. When we get up here to the higher latitudes, now that energy is coming in at a much higher angle. So since the angle is coming in, is going to disperse it so much more. Now it says low angle of incoming solar radiation. Remember, when we talked in class, you have your angle of incidence and your angle of incoming energy. So it's coming in at a certain angle. And when I'm saying a high angle, that just means that it's, coming in from, down below, it's spread out over a larger area. I'm not doing a very good job explaining this. If you would just simply say that the energy is spread out over a larger area due to the fact that the angle that it's coming in at is much greater at the higher latitudes, you'd be fine, right? Now, the other thing this is going to affect are our seasons. Remember how the Earth is tilted on its axis. Solar insolation deals with not only the unequal heating of the planet's surface, but it's also going to deal with the seasons. And as the Earth is tilted, that's going to affect this energy coming in. If we look during our equinoxes, we have direct sunlight coming in. We have half the planet in sunlight, half the planet in dark. So this would be the dark side, this would be the light side. When we look at the other equinox, again, equal day and night, now we have the dark side and light side. When we look at the solstices, that's going to be where we're going to be at our maximums. Maximum amount of daylight in the north, minimum amount of daylight in the south for our summer solstice. And that's because, again, the axis is tilted here. So again, we have almost direct energy hitting near the equator, very indirect energy hitting up here at the poles. But since the planet is tilted towards the sun, now we have our summer in the northern hemisphere because we have more sunlight hitting the north than we do in the south. We can see here in the south, we have parts of the southern hemisphere that are getting no sunlight whatsoever because there's no sunlight hitting it. Then when we flip, now northern hemisphere is tilted away, so we experience our winter here. Southern hemisphere would be in the summer though. So it's important to note, not only do we have, the different tilt of the planet causing our seasons, the southern hemisphere has the opposite effect of it. So we're experiencing our winter in December, but the southern hemisphere, if you look, is much more illuminated. So they're in the summer, we're in the winter. Then we're tilted towards the sun, so we're in the summer here, they're in the winter here. Then when we look at the equinoxes, summer into winter is the fall transition. We're in the fall, they're in the spring. Because again, they're going from winter to summer. Then down here, we're going from winter to summer. So we're experiencing our spring. They're experiencing their fall. So the seasons are the opposite in the southern hemisphere. And again, that's all due to the fact that the Earth is tilted on an axis, and again, we're not receiving equal sunlight across the planet. Even if the Earth was not tilted, we would still experience this difference in solar energy. It becomes more intensified when we think about the fact that we're tilted. So again, most direct sunlight, most energy per unit area at the equator. That energy per unit area decreases due to the angle of the sun changing and hitting less directly at the poles and the higher latitudes than it does at the equator. Oops. So why is that important to us? It's going to be what creates our winds. The unequal heating of the Earth creates and generates winds, and it's due to the convection process. Warm air is going to heat up. As warm air heats up, it expands. It's like a hot air balloon. It becomes less dense. As it becomes less dense, it starts to rise up into the sky. So since it's rising up, it's pulling its mass off the ground. Since it's pulling its mass off the ground, we end up with a low pressure area. Right? As that air cools off, it starts to sink down because it becomes more dense. As it becomes more dense, it sinks and puts more pressure onto the ground. So this would be an area, it says low pressure here, it shouldn't, it should say high pressure. And that difference between the pressures, the high pressure from the air stacking up and pushing more down onto it, that high pressure area and low pressure area are going to try to equalize. So you're always going to have the high pressure pushing towards the low pressure. And the same thing, the opposite's happening here. Since the air is rising, we get a slightly higher pressure up here, a slightly lower pressure over here, and we have a sideways movement up here. So we can see we end up with a circular pattern to our air. That's that convection process. So why is that important? That's what's going to distribute our heat across our planet, our moisture across our planet, and all those different things that we need. So when we look at it on a global scale, that was at a local scale. On the global scale, this is where we get into those convection currents. And College Board did a pretty good job saying, don't get bogged down in minute details. Don't worry that we have a Hadley cell and a Ferrel cell and a polar cell in each of the hemispheres. Understand the process more than the specifics. If you have a table or a chart given to you, that's where you want to list specific things. But if you can describe the process or explain the process, you're going to get the points. So here we're looking at describing what's happening in this red circle. We have hot air at the equator, since the air at the equator is heated the most because it's getting the most direct sunlight, the most concentrated energy per unit area is happening at the equator. The air is going to heat up there more than other parts of the planet. Board just went dead here. So as that air is heating up more than other places of the planet, it starts to rise up into the atmosphere. As it rises up, again, it's going to create a low pressure center here. As that low pressure center is created from that air rising up, the air is going to start wrapping around the planet and cooling off as it does that. As it cools off, the least heated up area of the planet are the poles. So this is going to be the coldest part. This is the hottest part. So the hottest part is going to allow the air to rise. The coldest part is going to be where the air sinks. That descending air that sinks down creates a high pressure center. Anytime you have a difference in temperature, you're going to have a difference in pressure. So the high always tries to equal the low. So the high moves towards the low, and we get that convection occurring. That circular path that the air is taking. And it's all due to the unequal heating of the earth from that solar insolation. So hopefully that makes sense. Now, they can ask you about more specific details to it, but if you can explain what's forming that convection cell, you're probably going to get the points for it, because they're not going to ask you specifically what forms the Ferrel cell. They're going to say, describe and explain the process of convection and why solar insolation is linked to that. That's what you'd have to do here. So we're going to connect that now to our next part, which is going to be climate. That air rising and cooling is going to cause a bunch of different things. So take a second, pause your video here, and see if you can explain what this graph is showing. Now, when you're doing this, first thing you want to do is look to see if the graph has a title. In this case, it doesn't have a title. So the next thing you want to do is look at the axis labels and see what they're labeled as to see what's happening with the graph. Then after you understand what the graph is showing as far as the labels of the axis, then look at the trend of the line to explain it. So go ahead, break the graph apart like that, and then explain what the graph is showing. And again, with an explain answer, you're explaining it and supporting that with detail. So hopefully you guys found that the graph is showing how as temperature changes, the amount of moisture that the air can hold changes as well. We can see that would be the describe part. The explanation then is going to be where you're supporting it with evidence from the graph. We can see at the lowest temperatures, our air moisture holding capacity is the lowest. But as our temperature increases, the amount of moisture the air can hold also increases. Got it? That's what you guys would want to do with this. If you wanted to cite specific points, say at 0 degrees temperature, and again, if you expand this out, this would be Fahrenheit. So at 0 Fahrenheit, we can see that we have, whatever this would be, 0.1 pounds of water per 1,000 cubic feet of air. When you're giving specific data points, again, make sure you're matching it to the unit that it's from the graph. So at 0 degrees Fahrenheit, we can see that we have approximately 1 pound of water per 1,000 cubic feet of air. By the time we go up to 100 degrees Fahrenheit, now we're at 2.9 pounds of water per 1,000 cubic feet of air. So you can see as temperature increases, water holding capacity is also increasing. That's what the explain part would be. So why is that important to us? As we have our air temperature getting colder, the volume of the air is going to decrease, because again, warmer air molecules start moving around, that kinetic molecular theory kicks in, and they start to expand. So we have our highest temperature here, our lowest temperature down here. And the reason that graph works the way it does, at the highest temperature, our air expands, and this is going to be our water vapor. And I have a constant amount of water vapor in different temperatures of air here. So we can see as our temperature of our air gets colder and colder and colder, the ability for it to hold the same amount of water vapor isn't there. It's going to decrease the amount of its ability to hold water vapor because our volume is getting lower and lower. Here we can hold all the water easily. Here we can hold the water, but it's getting very, very close to being maximum saturation. Here our air has shrunk down so much that we can't hold all the water that we used to, and this is where we start to have the rain or snow falling. The extra water vapor that's no longer able to be held falls as precipitation. And that's why, again, changing temperature dictates our weather patterns. When the temperature of the gases decrease, the solubility of water in it decreases as well, and we end up with precipitation. That's what's fueling the rain shadow effect. Warm, moisture-rich air comes in from the ocean. As it goes up the mountain ranges, elevation is changing, so the temperature decreases. As the temperature decreases, the ability for that air to hold on to the same amount of water drastically decreases. So all that extra water falls as precipitation. By the time it gets over to the top, now the water vapor is all out of the air. It's going down the other side of the mountain, warming up and trying to find more water to hold on to, because now it has the ability to hold on to more because the air is warmed up and expanded. That's what's creating the rain shadow effect. That's the depth you would want to go into if it was asking you to explain why the rain shadow effect works the way it does. So our check for learning, this part of the unit is done. Can you describe the structure and composition of the Earth's atmosphere? Can you explain how environmental factors can result in atmospheric circulation? And can you explain the sun's energies effect on the Earth's surface, as well as describing how Earth's geography affects weather and climate? Again, this last one, that's that elevation change. As the geography changes, as the elevation changes, temperature is going to decrease. As temperature decreases, the ability for it to hold on to the water decreases as well, and we have increased precipitation. All right, these other ones, again, if you can't do those yet, make sure you're going back, relooking. If you still can't do them after you rewatch it, email me. Hit me up over Google Classroom. I will definitely take as much time to explain it to you as you need. So thanks for watching. We'll pick back up with our last part here in a second.